Now, please join me in welcoming Joe and Chandrani with their talk.
All right. So welcome everyone to the last session in between you and happy hour. Today we're going to talk about a big question. So what if your security team could automatically fix your code vulnerabilities? So think about this. AI can go through code faster than any human, potentially finding and fixing your vulnerabilities. But we know that AI fixes are still imperfect, and we need to manage our expectations about the performance of AI fixes. According to a SW benchmark, even ChatGPT-4 could only fix about 2% of complex bug fixes. So that means we need to use AI with oversight and still keep humans in loop. And today we're going to talk about strategies for increasing our chances of finding and fixing correctly. And we're going to talk about where to focus effort. And this problem is actually two distinct issues. This is finding vulnerabilities and fixing them. And next, we're going to give you a little background on finding vulnerabilities in the traditional fashion. So traditional methods of finding vulnerabilities are going to be through manual code reviews, static application security testing or SAST, DAST, fuzzing, external bug bounty programs, incident reports, pen testing, or red team reports. The issues with this is oftentimes you have a lot of false positives generated, and this can erode developer trust when they see a potential vulnerability that isn't actually there. Additionally, you have a coverage of vulnerabilities can vary depending on the type of detection you're using. This process can be time consuming, and manual reviews are slow and prone to human error. And incident reports, like the known slice there, are the ones that you don't want. And we're going to see if we can use AI in this process. And the goal state of this is we want to be able to increase our coverage and increase our true positives and decrease our false positives. We're still not going to be perfect in our coverage of all vulnerabilities in this. And there are at least two ways of finding vulnerabilities using AI. We can do an AI-only approach, and that would be just using a prompt and feeding in your code to the prompts, or we can do some sort of fine-tune model like GPT 3.5 fine-tuning. And we tried this with a few hundred examples of real vulnerabilities and fixes, and it wasn't that great. And then you can additionally use a prompt-driven strategy where you're also using that to supplement your results from SAST and use AI. And then where can you do this in the process? You can do this at the stage of pull requests, or you can check your code retrospectively. You can do your whole code base. You can do entire repos. And that's a little bit harder of a challenge, but that's what we did. But the key is you can build on your existing frameworks and not totally throw them to the wind. And now we're going to talk about non-AI fixes. So as you can see, traditional methods of fixing vulnerabilities without AI are just people in seats doing work. There are problems of prioritization. A lot of times you don't know what priorities your vulnerability should face, your vulnerability should use, and then also you need a skilled team. Fixes are time consuming. Humans are also prone to error. And then you can have an example of instances where your team issues a patch for vulnerability, the patch didn't work, your team has to issue another patch. Also, you can have the same type of vulnerability can show up across multiple repositories if a bug bounty hunter finds one and runs it across all of your different products. But using AI, we know that we can use AI to generate fixes for at least simple code vulnerabilities. And we would still have the human validate the fixes. And we still need our expert team, but now they have more time to resolve the complex fixes AI can't handle. So there are commercial solutions out there, but we're going to talk about why you might want to build your own solution. A lot of times you will almost always have proprietary coding languages, styles, and libraries. For instance, your team may have a XSS fixing library that you want to make sure that your data gets sanitized, and you don't want to depend on an open source solution where you're not sure if it's going to be maintained. There's a large cost associated with commercial solutions. If you have a team of hundreds to thousands of developers checking in code, the cost for using a commercial solution can run into millions of dollars a year. One of the most important parts is you want to be able to customize the measurability of your fixes. You want to be able to measure your historical performance based on finding vulnerabilities and fixing them. And a lot of times you have those resources at your disposal. If you're tracking your fixes through Jira and GitHub, then you can automatically extract those programmatically. And finally, you want to be able to grow internal expertise in AI. This is important because you don't want to be dependent on commercial solutions. So with this, I will pass it over to Chandrani.
Thanks, Joe. So now we talk about the solution journey. This was very new area for us. We did not really know what would actually work, what would give us a good result. So there was a lot of trial and error before we could say, yeah, okay, this is an accepted good solution. Right. And then whatever work we are presenting here and the results, they are done on the GPT-4. But then it should be language model agnostic, the methodology. So first we started we needed to do a POC, right? We needed to establish the fact that this very thing that we are trying, trying LLM to find vulnerability and fix it, this would actually work. So for this, what we started with a zero-shot prompt engineering method. Therein, what you do is you rely on what the model already knows, the intrinsic knowledge of the model, and you are relying that the model will give you the most optimized results. Right. So as an input, we created a dummy repo with some very obvious, straightforward vulnerabilities in it. And we were like, okay, find and fix whatever you can. Obviously, the system prompt was not as simple. Just before the talk, I think by OpenAI, they mentioned that you need to praise your model. So we did the same thing. You mentioned you are a very expert AI security engineer. You're very methodical and blah, blah, blah. So, and then it was able to find out all the 8 to 10 vulnerabilities that we had injected with a very good precision, and then it was able to find great fixes for them. So with high hopes, we wanted to apply the same technique on our production repo, right? So it still is zero shot. But then the input strategy, we changed it okay, let's go on to the production repo and let's see what it gives. On the system prompt, we are not giving any additional example or any additional context, but then we are making it a little bit advanced. That means that we looked through our Jira, we found out what are the top 15 vulnerabilities. We picked those and we are like, okay, give me only the vulnerabilities related to this. We gave a list of languages so that when it is generating the fix, it is context aware. It has that language awareness. And we also gave output response schema. So do not just give me blood out response. You give me only for these fields, only in this particular format. Right. So everything was, going great. It gave out a lot of issues in the format that we expected and all that. But when we tried to manually evaluate, when we were going through the results, the issues, there were a lot of false positives. And not only that, the fix it had generated, it was very much hallucinated, which means for example, it would say that include a sanitize function, but it would not actually include a proper definition of it. So then we kind of took it slow. We went with okay, let's give a single example to it. So single shot method is in wherein you give your model a single example how your output would look like, and you expect that your model will learn and will try to mimic that. So we changed our input strategy from going to the production code we changed over to Jira, because in Jira we already have our like vulnerabilities logged in. There are vulnerable code snippets that have been exploited, so those are also logged in. So we took that as an example. And there is also a related repo that is written, like in this repo we have found out. So we are giving a one code example and the related repo. Right. So here what we saw is if it is very similar, if the code is very similar, it is able to detect that. But then variable tracing within the same file was still a problem. Like, for example, if the variable has been defined somewhere, later it's accepting input, and then finally it has been used as window.out, URL and all that, it is still not able to make all that context. That was the one. And then also, even for like we have given one particular example of injection, but if it's injection and if the code is a little bit different, XHR related or stored injection, it's not able to detect properly. So then we moved on to the few shot method. Few shot is like when you not give just one, but like 3 to 5 examples, so that the model understand the context and the task better. So here we look through like, okay, in our Jira, if we say injection, like what are the different types of injection examples that we can find, and let's give that and see what how we are saying. Right. So here basically multiple injection examples you are giving. With this, we were seeing improvements in detection, in finding the vulnerabilities, but we would say that there was still a lot to go. What we could say an accepted fix. So almost at the same time, we came across a paper that was by Boston University that talked about this chain of thought method, wherein they have mentioned that they have done vulnerability detection with about 70% precision rate, wherein so this is basically how it works is you have a problem statement and you are explaining what is the problem. If you are giving a decision to the model, then you are also explaining like why you are taking the decision. So basically you are you want the model to think the way a human would think, and it would mimic that entire thought process. So here we are not only giving the Jira ticket summary and the description, but we are also giving an explanation. Like, for example, here is my vulnerable code snippet. Then next I'm giving that why I think this is vulnerable. So I'm explaining like, okay, this param input is coming from user input. If a malicious JavaScript is loaded, then when the window.url gets executed, that gets executed in your in your environment. And then I'm giving a proper fix. So I'm not only giving like sanitize this, but I'm also giving a like proper definition of that, like how that sanitize would look like, right? And I'm saying like why that that fix would work. So with this kind of thing, and for like we mainly tried so far the injection, we saw a lot of improvements both in detection and the quality of the fix that it was generating. But I should definitely mention that it is not for vulnerabilities that is spread across multiple files. It is for vulnerabilities that is contained within the same file. So reality check, definitely like from the point when we started with the dummy repo, it gave everything perfectly. Everything was able to, all the issues were, it was able to found 10 out of 10 till the point where we are today. There was a lot of realization, right? So challenges, as I mentioned, like for example, the complex vulnerabilities, like whenever it is spread across multiple files, multiple repos, then GPT would do really poorly. Then when we moved over to the production repo, there is no proper test file, right? Because you never know how many vulnerabilities are out there in your repo. We have static code checkers, but we all know that also produces false positives. So if you are if the my model is producing 10 issues, I do not know if the 10 is out of 100 or if the 10 is out of 20. So you never know the denominator. And then the correctness of the fix, right? So this is also like very subjective, like how deep, how accurate you want your fix. Like, for example, if you are using a function, if you're saying that you need to include a function, the proper function definition should be present. If there is a place for constructor, if there is an import statement, all those should be included as part of the code fix, right? It should not just say include this. There should be library imports of this. So there should be proper code for those. So how much deep we would go with the fix. So those are also like subjective. So next we move on to metrics and evaluation. Initially, when we started this, obviously we started with a manual evaluation. We will go through each of these findings and we would see like whether it's a correct fix. If it's a correct fix, whether the fix generated is is good enough. But then obviously with manual evaluation, you cannot scale. That's not accepted. So what we tried is the auto eval framework. So this is something LangChain provides. They have a lot of like eval framework, eval APIs or functions that they provide. The particular one that we used is the scoring evaluator. So basically what we did is we initially created a data set with vulnerable code and the corresponding good fix. We called this as a golden data set. And then we would take that same vulnerable code and run it through the LLM and it ask it to generate a fix, right? And then we would compare like how close that fix is with respect to the reference fix. And this is where that the LangChain accuracy calculator comes into picture. So basically, it lets you define the accuracy on a scale of 1 to 10. 10 means like you're fixed, the predicted one and the reference one, they're very context-wise and everything is very similar. 7 means there are minor differences and so on. So we decided like, okay, if the accuracy is looking like closer to 70%, we can say like, yeah, this is a good enough to go. And then we can accept the prompt and we go ahead with that, like generate code fix of similar type in other repos. For metrics, there are two types of metrics that we have considered so far. One is the precision, right? So precision is like if you have 10 issues, but you have only 4 of them are correct. So your precision is then 40%. And then accuracy, like how good your fix is. So with like all these methods and like prompt engineering methods that we have tried, we found that with chain of thought, it is giving us more promising results. Yeah, and then we have a demo. Over to you, Joe.
Yeah, so there were 3 different ways that we implemented this. First, we did a code fixing directly from a Slack-powered AI agent. And we also had an option of implementation where we had a CLI-based infrastructure where we would iterate over entire repos and then select and approve fixes for PRs later. But this one is the most simple. And this is just a simple command line where we issue the PR directly. And this is very short. It's about 25 seconds. So this is the fix happens and it explains the fix and why, what was vulnerable. And then this is the PR. And yeah, that's about it. So conclusions. We had quite the journey, and it's still ongoing. So for people who aren't familiar, this is representative of the Gartner hype cycle. So it's where your expectations are over time. So when I first saw this a few years ago, this really resonated with me. So when we started off at the beginning, we had our POC, and we had a lot of expectations. I thought this project would probably take a couple weeks, and we'd be done with it. And then when we started moving up with increasing code difficulty, increasing vulnerability difficulty, we still thought we could handle it. We did zero shot, we did single shot on real code, same with few shot. When we got to chain of thought, we were still getting the fixes we wanted that actually aligned with historical fixes using our proprietary code and libraries. They weren't just generic fixes, and we thought that this was great. But as the complexity of all the vulnerabilities and the different coding styles and the different files kept going, we were still using this manual evaluation process, and we realized that this was not a sustainable thing. And then when we transitioned over to the auto eval framework, that was, we realized that we were at a place where we're going to be moving up, and there's actually a path forward. So now we're at the point where we are we have a clear path to full productivity. And some prompt strategies that we learned along the way that ended up being pretty valuable, we'd like to share. So the first one is you always want to reduce opportunities for LLM laziness. And what you see in the upper right-hand corner there, that's an actual function provided that's supposed to be a fix from GPT-4. So that's not what you want. So your prompt should contain something like placeholder comments, ellipses, and other shortcuts will never be used in place of functional code, and maybe even more than once. The second strategy is you want to make sure that you have your proper output schema. You want to include your file formats, the schema details, and how you want your output fields. So this is just a snippet of a couple of fields you might want. And even if you have this specified, you still may get syntactically incorrect output from time to time. The final one is you want to reduce opportunities for LLM hallucinations. So you want to have output fields that the LLM can generate into instead of hallucinating. So having library imports as a field or method creation for a field. Or you can have language-specific fields that would only be used in context of a specific language, like constructor changes or something like that. And some key takeaways. Directed fixes are helpful. So the more hints you can provide to your LLM, the better your fix is going to be. And finding and fixing uncomplicated vulnerabilities is a simple task for an LLM. And this may seem obvious, but fix things that are 100% known to be vulnerable first. For instance, if you have results that are validated from a bug bounty program, you can use that as input to your prompt and get a fix quicker that way. Metrics are key. So regardless of whether you build or buy, you want to measure the effectiveness of fixes for your code. And so traditionally when you do evals, it's pretty simple. You have a question, you have an answer, and it's pretty easy to think about. But when you're trying to do evals with code, you have to think a little differently because code is not human language. So for evals, your question is your code and your fix is the answer. And your answer can depend on how narrow your question is. How much information do you want? And fine-tuning prompts can take you pretty far. Chain of thought, as we saw, was the best for performance. And well-designed prompts and output schemas are key. And lastly, humans are still gatekeepers, and you always want to keep humans in loop for final validation. And that's it.
All right. The audience has a few questions for you guys.
Okay.
First one, nice work. How do you manage the accuracy of the AI code fix? Do you maintain any evals data set?
Yeah. So we track all of the fixes and all the results we track in a table, so that way we can measure the performance over time.
The second question is, why not use SameGrep, which is open source?
Yeah, so a lot of times, so we have an internal solution that we can take the results from our static analysis and feed that into the LLM. So it's kind of like you're adding an additional filter on top of your results.
Which one was more effective, finding vulnerabilities or fixing them using AI?
Fixing. Yeah, fixing, because when you're trying to find something, it's pretty greenfield. You can look through an entire file, and a lot of times the LLM would generate a lot of false positives. A lot of times it'd be good at finding vulnerabilities, but it would find things that weren't there too. So yeah, the fixing, if it's more directed, if it had something more narrowly focused to look at, then it could do better.
What kind of vulnerabilities here you have experimented with?
Yeah.
Yeah, we have mainly tried with XSS injections. Yeah.
How does it handle when the fixes require a complex code fix?
Can you say that again?
How does it handle when the fixes require a complex code fix?
So yeah, I can take it and then you can add.
Totally.
You need to give a lot of details, like for example, specific to your company, what all standards it follows. So sometimes in the system prompt, you need to give those details as well. And then you need to mention in your output parsers, like where exactly you want, if there, like Joe mentioned, the import statements, if there are constructors, if there are functions, where exactly you want them to be placed. So it really depends how fine-grained you can make your system prompt. You want to add something?
When you do few shot, do you retrain the model or just provide the samples as context?
So we have something set up that was like, I called it an adaptive few shot. So depending on the type, if we knew the vulnerability type ahead of time, it would pull out the few shot examples from a known set of that particular vulnerability type.
How do you mitigate any security implications of giving AI access to production?
So we always would only issue PRs, so nothing would ever go to main. Yeah.
Have you considered any semi-automated feedback mechanism so the LLM responses can be refined over time in a scalable way?
Yeah, that is there in our plan. Like, for example, right now it's very much Jira driven, the flow we have done. So probably something like Jira comments, and then that incorporate that in the LLM in the backend. Yeah.
Were you worried about sending internal code over to external model APIs?
That's a great question. We did everything through Azure, OpenAI, our own company's instance. That was something we would have been concerned about normally.
All right. These are all the questions we have on Slido for now. Please join me in thanking our guest speakers.